Okay, so I've got two examples here of inequalities involving variables that are going to illustrate some of the issues that can come up with solving inequalities. Okay, so the first one, let's look at this one. 2 is less than 3x plus 1 over 2x plus 4. And we want to simplify it. We want to find the values of x that make that true. So what we're looking for are some expressions with x by itself on one side of the inequality. So the natural thing to do is to multiply through by the denominator here, 2x plus 4. Fine. If it's positive, we just multiply through the way we would if it was a regular equation. If 2x plus 4 is negative, we switch the sign of the inequality. But the problem is there's that x there, so we don't know whether it's less than or 0 or greater than 0. No problem. We just think about the two cases separately. It's kind of standard divide and conquer strategy, works in many contexts. So first of all, think about the first case. So case 1 is going to be the case where 2x plus 4 is greater than 0, positive number, don't have to worry about flipping anything. And to help us kind of stay grounded in what we're doing here, let's think about what that means for x. So that is the same as saying that 2x is greater than negative 4 or x is greater than negative 2. Okay, so when I'm thinking about case 1, it's easier for me to think about this is the case where x is a number greater than negative 2. So we're only thinking about that case right now. And if we're in that case, going back to the inequality, then we can multiply through by 2x plus 4. We know it's a positive number, so we can just do that. So multiplying through, we get 4x plus 8 is less than, leaving the inequality alone, no problem there, 3x plus 1. I'm going to put the terms with the x's by themselves on one side and the terms without x's on the other. Again, same thing I would be doing if this was an equation. So I'll get x is less than negative 7. Okay, that seems fine, but let's zoom out for a moment. Here's the problem. If we're in the case where x is greater than negative 2, x is greater than negative 2, x is a number bigger than negative 2, x cannot simultaneously be less than negative 7. Okay, these cannot both be true. What does that mean? It means that this case that we're looking at didn't give us any solutions for the inequality. Okay, so we have no, spell that right, no solutions from case 1. So that is what it is. Sometimes we get solutions, sometimes we don't. Let's go on now to, that was case 1. Now let's go on to case 2. Case 2 is when that denominator is negative, 2x plus 4 is less than 0. And we know from what we did up here that this happens when x is less than negative 2. Okay, that's this other case. And here's the case where we do have to switch that inequality. Okay, so we're going to do that. Again, we're going to take the thing we're looking at, we're going to multiply both sides by 2x plus 4, but because we're in the case now where that's a negative number, we're going to switch the direction of the inequality. Okay, so we still get 4x plus 8, but now because we've multiplied by a negative number, we switch that less than sign to a greater than sign, and now still got 3x plus 1. On the other side, the rest of the simplifying is just going to go the same as it did before. We're still going to get x on one side, negative 7, but now we're thinking about x being greater than negative 7. So when we're in the case where x is less than negative 2, the inequality we started with is true when x is greater than -7. Those two things can both be true. It's certainly possible for x to be less than -2 and greater than -7. Okay? So a way that we often put together two inequalities that have to simultaneously be true is we can write them as a double inequality. So you've probably seen people write things like this. We're saying is x has to be less than -2 and greater than -7. Okay. These are our solutions from case 2. These are the ranges of x that will make the inequality that we started with true. Okay. Now you might be thinking, wait, there's another case, right? We haven't thought about case 3. What about case 3? Ooh, case 3 is kind of a tricky case. What about the case where 2x plus 4 equals 0? Okay, that is a possibility here, and we know that that is going to be true when x equals -2. Well, what do we know about that? We know that there are no solutions for when that is true, because when that is true, our expression in question is undefined. Okay, we've got a 0 in the denominator. Okay, so this cannot be a solution. So overall, the thing we started with, maybe I'll just recopy it here, and maybe I'll switch back to my regular color. Let's not get too much red here. The overall answer here is that 2 less than 3x plus 1 over 2x plus 4 is true when x is less than -2 and greater than -7. Okay, so that's our overall solution here. And just as we've done before, it's never a bad idea to check that. So let's pick a number that's between -7 and -2. Oh, let's let x equal -3. And so what we want to know is when x equals -3, is that expression true? Is it true that 2, I'm putting a question mark here, is less than 3 times -3 plus 1 divided by 2 times -3 plus 4. That sounds like -9 plus 1 is -8. -6 plus 4 is -2. That overall equals +4. And yes, 2 is less than +4. That's good. Let's also check a case where we think it shouldn't work. Let's pick a number outside this, this range. 0 seems like a nice, easy number to pick. So if we have x equals 0, we ask ourselves, is it true that 2 is less than 0 plus 1 over 0 plus 4? And no, not true, but as expected. Okay. So these kinds of situations where you're working with an inequality and you have to multiply through by an expression that might be negative, might be positive, the way to handle it is to divide things up into cases. In this case, we only found solutions for one of them, but it's possible to find solutions in multiple cases. Within a case, all of the conditions have to be true. So within case 1, the reason why we didn't find any solutions is that there was no way for both the inequality that defines the case and the requirement that the inequality, that the thing we're trying to solve, gave. There was no way to make both of them true. So the fact that there was no way for this to be true and that to be true meant that there were no solutions. in case 2, we found a range of values of x for which both the inequality that defines the case and the inequality that comes from the problem we're trying to solve, they're both true. So within cases, both the things need to be true. Across cases, you can have either case 1 or case 2, which again, we didn't see in this problem, but you could see in this. All right, so let's go on to one other problem that illustrates a slightly different thing that you sometimes see in using inequalities. Okay, so this example is, what do I have here? Z squared, that's a z, minus 3z greater than or equal to 0. So again, we're not really approaching this any differently than we would if it was an equation. If this was an equation, what we would do is we would factor the left-hand side and then think about, okay, well, all it takes to make it equal 0 would be to have one value or the other equal 0. That's not totally irrelevant here. But with inequalities, again, it's a little bit more complicated because there's multiple ways that a product can be positive or negative. So start by factoring just the way we always would. So just rewriting that as z times z minus 3 greater than or equal to 0. Okay. So we've got two factors here. And what we're saying is this product of two things is positive. So this overall is positive if either z is greater than 0. Actually, I'm saying positive. You know what? Let's be more precise here. Positive isn't wrong, but it's incomplete. Positive sounds like it can't be 0, and what we have here is a weak inequality. So let's just be really nice and precise about that and say is non-negative. Okay. This side is greater than or equal to 0 because two possible ways for that to be true. First, if both factors are themselves non-negative. Okay. So z is a positive number and z minus 3 is a positive number. And second possibility is if they're both negative. If we have two negatives, we'll also get an overall positive number here. Again, being more precise, if we have two non-positive numbers, we'll get a non-negative number. You can see why people like to say greater than or equal to 0. The non-positive, non-negative is a little bit weird, in my opinion. But back to the main point here. The expression is non-negative if z is less than or equal to 0 and z is less than or equal to 3. Okay, I'm going to emphasize here that we also have an and. Okay, so here we have both factors are non-negative. One way you can get a non-negative product, but you could also get it if both factors are non-positive. Okay. So the inequality holds if either 1 or 2 is true. And 1 and 2 are both conditions where this thing and that thing have to be true. So just as I was saying before, you have ors connecting the cases. You could even, if you wanted to, think of this as case 1 or case 2. But within the case, both these things have to be true. Now, in both cases, there's some redundancy here. Okay, so let's go to a different color here. If z is greater than or equal to positive 3, it's automatically greater than or equal to 0. So really the only thing that matters here is if z is greater than or equal to 3. Okay, this is the relevant requirement. And similarly in case 2, if z is less than or equal to 0, we know it's less than or equal to -3. And answer this. It's the relative. So our overall solution is that z squared minus 3z is greater than or equal to 0 if z is greater than or equal to 3, or z is less than or equal to 0. Okay. Sometimes it's helpful to look at these kinds of solutions again with a number line. So let's just do that here. The numbers that we're interested in here are 0 and 3. Okay, and so case 1, let's do case 1 up here, so that the inequality could be true if z is greater than or equal to 0 and z is greater than or equal to 3. Okay, so both these things need to be true. So really what's relevant here is the place where both of the areas overlap. And similarly with the case 2 down below here, case 2, we can have all these values are where z is less than or equal to 0, and then putting -3. Sorry, no, we don't need to put -3 in. What are you doing? We don't need -3. It's still +3 here. Putting z less than or equal to 3. Here, they're both true. And z is less than or equal to 0. Okay. Final thing we might do here is pick some numbers and check. It says that the equation should be true when z is greater than or equal to 3. So let's think about checking here. Z equals 4. We would have 16 minus 12 greater than or equal to 0. Yes. If we had z less than or equal to 0, let's pick z equals -1. Here we get -1 squared is 1. -3z times -1 is +3. 1 greater than or equal to 0. Yes, that's also true. It says that outside of this range, if we have a z that is greater than 0 but less than 3, it shouldn't be true. So let's pick one in that range. Should not hold. If z equals, let's pick +1 here. 1 minus 3 greater than 0. No. And that is as predicted. Okay, so if there's kind of a bottom line message for dealing with inequalities in these kinds of contexts, it's to go slow, be conscious of your steps. If you feel like you're getting bogged down in the cases and managing multiple inequalities, it's never a bad idea to draw a number line and see whether inequalities are conflicting with each other or they're redundant or whether they really are separate requirements here. And if you can get to places where you can check your work, that's always worth doing too. So there's practice problems for you to work through on this. And I want to say those practice problems are bringing together all of the basic algebra skills that we've been doing throughout Unit 1. So if you can work through all of those problems, you should feel good about that. If you can work through the practice problems for Lesson 1E, you're in good shape to move on for the rest of Math Camp. Okay, see you then.